Okay, so today is going to be our last lesson for quadratic applications. There are lots and lots of applications of quadratics. The problems that we did last week with the area of rectangles, those were applications of quadratics, and there's many more, but again, we're trying to keep it as basic as possible since we're not together. But going into math too, you will learn a lot more applications of quadratics. But then one of the main applications is projectile motion. And projectile motion is a form of motion experienced by an object or particle, and that's why it's called a projectile, that is projected near the Earth's surface and moves along a curved path under the action of gravity alone. Some examples are football, baseball, tennis ball, rockets, all kinds of things that we could throw or project or toss. So if we were in class together, we would actually have a student come up to the front of the room and toss a ball up in the air and catch it, or toss it to some other students and talk about the different types of projectile motion. One of the hard things to understand is what if we took a ball and threw it directly straight up and then let it fall back and caught it? Well, if we looked at the path it took, it just went straight up and straight down. However, if you were to plot its height, so the height of the ball, according to the time it was in the air, not in terms of its horizontal distance, because it really didn't have any horizontal distance, it just went straight up and straight down, it would make a parabolic shape. In other words, it would make the shape of a parabola. So let me just show you this little applet, and what we're going to do is it's going to drop the ball. We're going to be on the Earth's surface. And watch what happens from the height of the ball according to the time the ball was in the air. Do you see how those parabolas are being formed? And this is not what the ball is actually doing. The ball is going straight up, straight down, straight up, straight down. But you see all these little parabolas being formed. And the reason why that's happening is because of the effect of gravity. When we, even if we kick a ball, and it does make a parabolic shape, but when we first kick it, the velocity behind the ball is that initial velocity. But as soon as that ball leaves the ground, the gravity starts working against it, which is what makes the ball slow down as it goes up. And then as the ball reaches its maximum height and starts to fall back to the ground, it speeds back up because gravity's working with it. And that is why these don't make like a V shape or a linear shape and the ball doesn't go, to outer space. It makes a parabolic shape because of the effect of gravity. Okay, so for what we're going to do in Math 1, it's going to be pretty simple. You are going to be given a function, and it'll tell you the function models the some height of an object after so many seconds. Sometimes it'll give you more information. For example, like this function, as you get older and take physics or honors pre-calculus, you'll learn more about it. This one must have been measured in meters per second, because that technically would have been negative 4.9, and it has to do with the gravitational constant, which is 9.8 meters per second squared. And then this 20 would have represented the initial velocity of the object, so it must have been moving at 20 meters per second. And then this 60 must represent the initial height. So let's draw a diagram of what's happening here. Okay, so in my diagram, I'm mainly going to only draw the first quadrant because that's what makes sense in the context of the problem. It doesn't make sense to have a negative time. So we're only going to be looking at the part of the parabola that would be represented in this first quadrant. Because of what we have learned about quadratic functions, we know that this parabola opens downward because the leading coefficient is negative, and we also know that the y-intercept is at 60. So if I was to mark that on here, it would start at 60, and obviously it's going to go up and it's going to come back down because the object, whatever it is, even if it went straight up and straight down, remember it's going to make this parabolic shape because of the effect of gravity. And again, we're not plotting its actual displacement, we're plotting how high the object was according to time. Let's make sure that we label this so that when we go to answer our questions, we know, that this x-axis, which we're going to call t, represents our seconds, And the y-axis would represent the approximate height. And I'm just going to go ahead and tell you, in this case, our height is going to be measured in meters. I know that it didn't tell us, but I'm going to tell you that it's measured in meters. So it's the height of the object. All right, to be able to answer the next set of questions, there are lots of algebraic ways we can do it, but we are going to use our technology. So we're going to use Desmos to answer this. Okay, so I've just gone into Desmos and I've typed in y equals negative 5x squared plus 20x plus 60. Obviously, I can't see everything I want to see, so I'm going to go in here and manipulate that in my, my window. So I'm going to cut off those minor grid lines. And I'm not real sure exactly how high this goes. So you can kind of just play with it and type in some numbers. Obviously, maybe I say, let's go to 100. And I just kind of see what happens. And then I might just click and slide around. You can use zoom in, zoom out. That's not my favorite, but just make sure that you can see the main part of the parabola. Then you want to start looking for the key features of the parabola. So guys, our key features are things like the vertex, the x-intercepts, the y-intercept. These are our key features of our graph. So if we come up here and we click on this vertex, it's going to tell us what it is because Desmos knows that these are the key features. So that is the point 280. And then we can come click right here and we can see that we have an x-intercept at 6. 0 or root at 6. We also have one at negative 2. But think about it, that negative 2 is really not going to mean anything in the context of the problem because we're not going to talk about negative seconds. We're really only looking in that first quadrant. You can also see that the y-intercept is at 60. So let's go put those things on our graph. All right, so let's get into answering some questions. How long does it take the object to reach its maximum height? And what is the maximum height the object reaches? All right, so you have to think about which one of these key features is going to answer that question. Is it going to be the y-intercept? Would that be the maximum height of the object? No, that would be the initial height of the object. Would it be the x-intercept? No, the x-intercept is when the object reaches a height of 0. In other words, when the object reaches the ground. Would it be the vertex? Yes, because the vertex is the highest point on the graph. So anytime you have a question about how long did it take to reach a maximum height or what is the maximum height, we are going to be looking at that vertex. So let's label this stuff. All right, so how long does it take for the object to reach the maximum height? All right, so guys, the question is how long. If the question is how long, they're asking for the time. So you got to remember that the x values represent time and the y values represent height. So when we're looking at this vertex right here, the 2 represents the time where the 80 represents the height. And I'm just going to put h there for height. So when it says how long does it take for the object to reach its maximum height, the correct answer would be 2 seconds. Then it goes on to say, what is the maximum height the object reaches? Again, we're still talking about that maximum up here. What was the highest height it reached? So that would be the 80. And then remember, I know the problem didn't say it, but we're going to use meters. So we would say 80 meters. Then the next question is, how many seconds does it take for the object to hit the ground? Okay, well guys, if you reach the x-axis, or in this case we call it the t-axis, that is when the height has reached 0. So that would be when the object reaches the ground. Again, it's asking how many seconds. It's asking for a time. And that was that x-intercept we got from Desmos, which would be 6 seconds. And this is a really good question, and you're not going to have this question in your Delta Math assignment, but it says, what is the practical domain of the problem? Well, we talked about in yesterday's lesson, or sorry, Tuesday's lesson, that the domain of a quadratic is all real numbers. But now we're talking about the practical domain of this problem. Obviously, this object wasn't in the air for a negative amount of seconds. When we started at 60 meters off the ground, that was at 0 seconds. And then the object lands on the ground 6 seconds later. So once it lands, it's over. It's not still in the air. It's not drilling itself into the ground. So this is how we figure out that practical domain. The practical domain would be between 0 and 6 seconds. So if we wrote it in words, we would just write that. Between 0 and 6 seconds. If we wrote it mathematically, we would use that interval notation. 0 is less than or equal to t is less than or equal to 6. Okay, let's do another problem. A rocket is launched from 180 feet above the ground at time t equals 0. The function that models this situation is given by h of t equals negative 16t squared plus 96t plus 180, where t is measured in seconds and h is the height above the ground measured in feet. Draw a sketch and label the important features. All right, well guys, before we even go into Desmos, we know that this is going to open downward because it has a negative leading coefficient. Plus, think about it. It's a rocket being launched. It's going to go up and then come back down. And so you don't really need Desmos to do the sketch. You're just kind of doing that sketch of that piece of the parabola. We also know that it starts at 180. It tells us the initial height is 180, plus we can see that y-intercept right there of 180, so we can mark that on our screen. All right, so we know the initial height is at 180 feet. We don't even need technology to figure that out. That's that y-intercept. We know the object's going to go up and come back down. Now, obviously, this parabola, like if you graph the whole function, does keep going, but that just doesn't make sense in the context of the problem. In the context of the problem, we're going to start at 0 seconds. Now, we aren't quite sure yet when it will hit that ground. So let's go to Desmos, and let's type this function in. And let's go ahead and figure out some of those key features there. So again, if I come right here and I click, the Desmos is going to work for me because it knows I'm looking for that y-intercept. And then if I come up here, it's going to give me that vertex at 324. And if I come down here, it'll give me that x-intercept at 7.5. All you got to do is hover and it'll show you those key features. All right, so the first question, what is the practical domain for t in this context and why? All right, guys, remember domain is our x values, not our y values. So the practical domain would be from 0 seconds to 7.5 seconds. And if we write that mathematically, we'd say 0 is less than or equal to t is less than or equal to 7.5. Why? Because the object is in the air from 0 seconds to the rocket is in the air from 0 seconds to 7.5 seconds. And once the rocket hits the ground, the whole project's over. Shooting the rocket's over. It's done with. All right, so the next question. What is the height of the rocket 2 seconds after it was launched? What is the maximum value of the function and what does it mean in the context? When is the rocket 100 feet above the ground? When is the rocket 250 feet above the ground? Wow, okay, we're getting into some questions here. So what I'm going to do is go back to Desmos and see what we can create. All right, so remember in Desmos, we can always click our bolt and duplicate our function and then make a table. Again, these negative values do not make sense in the context of the problem, so I'm just going to delete them. And then I'm going to come down here to 2, and I'm just going to keep pressing enter so that I can see what some of these things are showing me. Now, we already know that this rocket hits the ground at 7.5 seconds, so if you want to see that 0 in there, you could type right here 7.5, and we know that these are the values that we wanted to look at in between. So the first question it asked us was, what is the height of the rocket 2 seconds after it is launched? We can answer that right here from creating our table. It was 308 feet in the air. And so we would just jot that down. What is the maximum value of the function and what does it mean in context? Well, guys, the maximum value of a function is always the y value of your vertex. If you have a parabola that opens upward, it would be the minimum value of the function. So the actual maximum value of the function is the 324. So what does that mean in context? It means the maximum height reached by the object is 324 feet. And these are the questions you're going to have in your Delta Math today. It's going to be like, how long did it take for the object to hit the ground? Then you're going to be answering the x-intercept. What was the maximum height reached by the object? That would be the 324 feet. Now, if it then said, how long did it take to reach its maximum height? That would then be the x value of the vertex. So I'm just going to add that on here. So again, if the question was how long did it take to reach its maximum height, that would be 3 seconds. Okay, I'm going to skip down real quick to some of the questions at the bottom. What are the intercepts of this function, and what do they mean in the context of this problem? All right, well, again, we wouldn't worry about this intercept over here, and I don't even remember what it was looking at Desmos because it's not in the context. The intercepts we would be talking about is the 7.5 and the 180, the x-intercept and the y-intercept here. So what does the 180 stand for in the context of the problem? The y-intercept of 180 is the initial height of the rocket. So it's the rocket's initial height. Maybe it's being shot off of the top of a building or a really large stage, or who knows, but it's originally 180 feet off the ground. And then the other intercept that's important in the context of the problem is the x-intercept of 7.5. Again, I know there's two x-intercepts, but the other one's negative, so it doesn't make sense. And that represents how long it took for the object to reach the ground, how long it took for the rocket to reach the ground. So the rocket, it was in the air for 7.5 seconds. Or it might be, it took 7.5 seconds for the rocket to reach the ground. You're not going to have questions like part E, F, and G, and I in your practice today, but I do want to just show you how you could answer questions like that. If it had asked, when is the rocket 100 feet off the ground, what we would do is just go into Desmos here, and we'd add that in, y equals 100, because remember, y represents our height. Now, I want you to think about it. This intersection right here wouldn't make any sense because it's not in the context of the problem. We don't even look back here. We don't have negative seconds. But this one would. So what we would do is we would say, you know, it took about 6.74 seconds for the object to fall back to 100 feet. If we then change that to 250 feet, notice there's two intersections. There's one here at about 0.85 and another one at about 5.15. And so there's two different times that the rocket reaches a height of 250 feet. It reaches that height on the way up, and it also reaches that height when it's falling back towards the ground. So that question of why is there only one answer for when it reached 100 feet versus two answers for when it reached 250 feet is because it only reaches 100 feet on the way back down, but it reaches 250 feet on the way up and the way back down. Okay, so let's look at a delta math question. A company is selling widgets. The amount of profit Y made by the company is related to the selling price of each widget X by the given equation. Using this equation, find out the maximum amount of profit the company can make to the nearest dollar. So folks, it is asking for the maximum amount of profit. Immediately you know you need to find the maximum of this function, which is the vertex. Then also notice it's asking for the maximum amount of profit. The profit is represented by the Y value. So we want the maximum value. So we're going to go into Desmos. We're going to type this in. You're going to be like, what? I don't see it. So just start trying to zoom out, and kind of play with it for a while. And it's just one of those things that you have to play with. You're not going to know exactly where to put it, but we know we need to see that maximum. So what I would do is then go into your wrench, because sometimes if you zoom out a lot, it makes the parabola so small you can't see it. And then just start making up numbers. Okay, I don't know, is it 500? Woo, wait, I put way too much in there. Is it 500? Oh yeah, that shows it to me. That worked out. If not, make it bigger. If not, make it smaller. And then you come up and you hover until you find that. Now, this says that it would be at 461.125. And if I go back, it says to the nearest dollar. So if we are doing this to the nearest dollar, that would then be 461. So let's go type that in. Submit our answer. And then it'll show you that you're just finding the maximum there to the nearest value. All right, so let's read one more. A rocket is launched from a tower. The height of the rocket, y, in feet is related to the time after the launch, x, in seconds, by the given equation. Using this equation, find the time that the rocket will hit the ground to the nearest hundredth of a second. Okay, now guys, in this case, it's not to the nearest second, it's the nearest hundredth of a second. So remember, that's 2 decimal places. So again, we're going to go over to Desmos and we're going to type this in. Make sure you pay attention to what this question is asking. This time it's saying, find the time that the rocket will hit the ground. So it's not asking for the time it takes to reach its maximum height or for the maximum height. It has nothing to do with maximum, so this is not a vertex question. When the rocket hits the ground, that is the x-intercept. Now remember, we wouldn't use this x-intercept over here because that doesn't make any sense in the context of the problem. It would need to be this one. And it asks us to do it to the nearest hundredth. So that's 2 decimal places. So if this is 12.716, we need to round that. And since 6 is greater than 5, we're going to round this to 12.72. And that would be the answer that we would type in. And again, you don't type in seconds. It knows it's seconds. You only type in the answer. Submit your answer. And it goes back over to it. Remember, when it hits the ground, that is a height of 0. So technically, you are finding that x-intercept when this equals 0 in the context of the problem. And only this answer makes sense. The other answer does not make sense. All right, good luck. You got 5 of these to do. And then we will be moving into statistics.